In this video, I'm going to go over the Exploration 8-4B when we first started practicing writing these equations for the combined sinusoids. And so what I would do right away when you approach one of these problems is decide what's changing, either the amplitude or the sinusoidal axis. And I can see right here that the x-axis is no longer the center for this curve, which tells me that the sinusoidal axis is changing, which means I'm going to add two sinusoids. With this one, the x-axis, it still remains the center of the sinusoid, and I can see that the amplitude is changing as the sinusoid continues. So I'm multiplying two trig functions, or two sinusoids. With the next two, here's another one. The amplitude, this distance is staying the same, but it's now following another sinusoid instead of the x-axis. And so that means that we are going to add two sinusoids. And then with this bottom one, amplitude is changing, so we are going to multiply two sinusoids. So before you start these problems, I'd highly recommend drawing in the larger sinusoid. And so it's hard to find this exact center, because if you look at the top, I can see that it hits up at 6, but then right here, it looks to be an uneven amount, and so it looks like it's about 4 and another little piece. Well, keep in mind that this curve is moving. It's trying to follow a sinusoid. So this point is going to be a little bit lower than what it would be if you were to take this entire curve and straighten it out. And so even though this looks to be a little more than 4, I'm going to say that the overall height is 4 if I were to straighten this out, which means that the middle would be 2 below that maximum. So this is where my sinusoidal axis is going to start. It's going to need to cross through this inflection point between this max and min right here. Again, here's the minimum point. It's going to be 2 above it. Another inflection point. Right here, it's going to be 2 below. And that should give us enough information to make the sketch of the larger sinusoid. So now from here, I can see that this curve is a cosine since it's starting not at the origin. And so it's starting up at +4, which means that the amplitude is 4 cosine. And then notice that the cycle size, it ends at 90 degrees, which means that it's 4 times smaller than a normal cycle of 360. And so you could do that off to the side. 90 over 360, it's a fourth of the size. So in the equation, we put in the reciprocal. So I'm going to take 4 cosine of 4 theta, and we chose to add, since the sinusoidal axis is what's changing each time. And now the harder part is to find the equation for the smaller sinusoid. And so I can see that it's 2 above the sinusoidal axis, which tells me that my amplitude is 2. Since it's starting above the sinusoidal axis and not at the sinusoidal axis or at the origin, I know that this is a cosine function. And then the next part is I need to figure out how much smaller this curve has become. And so I'm going to count the cycles, and this is 1, 2, 3, 4, 5, 6, 7. So I have 7 cycles in 90 degrees. Well, if I thought then in 360, that would be 4 times more cycles, so I would have 28 cycles in 360 if I were to continue this graph. And so I will put in 28 theta. For the second one, same idea. I would recommend drawing in the larger sinusoid first. And so you can see it's going to follow all of these minimums and maximums, since this large curve is what sets the amplitude for the smaller one. So that's 1 full cycle. Again, I can see that this is cosine since it's not starting at the origin, and it's starting at 5, so it'll be 5 cosine. 1 full cycle takes 120. 120 over 360, that means I'm making it a third of the normal size, so this will be 3 theta. We know that we're going to be multiplying since it's the amplitude that's what's changing. And so now we need to find the equation of this smaller curve. So since it's starting at the origin, I know that this is a sine function. And keep in mind that this is the amplitude of the sine function, this cosine curve, so I don't need to worry about a number in front. And now to count the cycles for sine, it's a little bit tougher, because right here is a part of a cycle. From here to here would be 1 full cycle. This would then be 2. This is where it gets kind of confusing, down in here where it gets small and it's really hard to tell where it hits. And so once you see the spacing between these 2 points, that helps you place another point to keep that spacing the same. So far this is 1 full cycle, 2 full cycles, 3, 4, 5, 6, 7, 8. This would be about 9, 10, 11. But then we have this leftover piece right here. And so this leftover piece and this piece end up making a full cycle. And so we'll count this as 1 because this chunk and this chunk match up to make 1 full cycle. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now keep in mind that we have 12 cycles in 120 degrees. Well, that means that in 360 degrees, I would have to have 3 times the amount, so 36 cycles. So that means we made these little curves are 36 times smaller than normal. So in the equation, we will have 36 theta. So now the next 2 get a little bit tougher because then we are in radian mode. Notice the x's. Notice how the x-axis is labeled, and so we are in radians. This first one, we decided that the sinusoidal axis is changing, so I'm going to go ahead and sketch that in. And so again, it is kind of hard to find where that perfect middle is going to be, because right here it looks like the maximum is at 3. The minimum looks to be about like 2.75. But keep in mind, if we were to take this curve and push it down to straighten it out, that this would more than likely be an overall height of 6, which would mean that the amplitude is 3. So I'm going to start at the origin. Right here is the maximum. I'm going to go 3 below. Let's see, another point that we could mark right here. We could go 3 below. Right here we could go 3 above. Over here 3 below. So that would probably give us a good enough set of points to make 1 full cycle here. And so there's the middle of our curve. I'm going to go ahead and write the equation for this one first, and I can see that it's going to be sine since it's starting at the origin. The maximum that it'll ever be is 2, so that is the amplitude. And it's finishing in 8 radians. So keep in mind that now the period is 8 radians. It's normally 2 pi radians. So this is the dilation factor. So in my equation, I'm going to do the reciprocal, which is 2 pi over 8, or that would be the same thing as pi over 4 if you wanted to reduce it, either way. And since we're in radians, I'm going to use an x, and we are going to multiply that by the equation of the smaller one. So the smaller sinusoid, notice it's starting above the sinusoidal axis, so that tells me it's cosine, and it's always saying 3 above and 3 below. So I'm going to have 3 cosine, and now we need to count how many cycles. So here's one of those U-shapes, so that's 1, 2, 3, 4, 5. And I'm just going to stop there since it stopped at a nice amount. So I can see 5 cycles in 2 radians. Normally we would want to see this in how many in 2 pi, but that's not how my scale is labeled. And so I'm going to come over here and write a proportion. I have 5 cycles in 2 radians. I need to know for my equation how much smaller we made it, how many cycles are in 2 pi radians. And so to solve this proportion, you could multiply across the equal sign, okay, so cross multiply, and then you could solve for x that way. Or you could look at this and say, well, if 5 cycles are in 2 radians, there should be 5 pi cycles in 2 pi radians. So I'm going to have a 5 pi, and then again an x. With this last one, we know that the amplitude's changing, so again, you'll want to sketch the larger sinusoid, at least do 1 full cycle. I got a little off right there. Same thing here and here. There's 1 full cycle. And you want to identify those points, those tangent points. So you can see each of these here is where it's tangent. And again, it's harder to figure out, especially since I messed up my drawing a little bit. But look at the spacing between the dots, and that's going to help you figure out where you need to place new ones. So there'd be a point here and here. So this would represent one cycle. This would represent another one, even though it's such a weird shape. Here's another here, another here, and another here. Okay, so notice that this is a cycle. This is a leftover piece of a cycle that combined with this little piece would make one full cycle. So once you count the dots, you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I know that this smaller one will have 13 different cycles in there now that I've sketched those dots. So we'll come back to that here in a second. The equation for this larger curve starting at the origin, so I know it's going to be a sine function. It goes up to 6, so there's my amplitude. And then it finishes in 2 pi. So my cycle is unchanged, so I'll just use the x there. I'm going to multiply this by the equation of the smaller one, and you can see it's starting at the origin, so again another sine function. And we counted 13 cycles in 2 pi. That means it's 13 times smaller, and then we use an x. The difference between these two is I have the normal cycle size of 2 pi on this grid. So I can see how many cycles there are compared to the normal cycle of 2 pi. What made this one harder is that I don't have it labeled in terms of pi. So I can't see how many cycles there are between 2 pi because that would be somewhere around in here. That's why we had to set up this proportion to figure out how many cycles would there be in between 0 and 2 pi.